Good afternoon, Algebra 2 Trig Honors class today. So I would like to talk about some of the simple questions for the Chapter 4 test. Again, Chapter 4 is all about polynomial, so we'll take a look at that. So the first one is about finding the end behavior of a polynomial. As you can see that this one is considered a fifth degree. 1, 2, 3, 4, 4 term, it's a quadnomial, so fifth degree quadnomial. So the way to find out the end behavior is always taking out the term with the greatest power. So once we take out the greatest power, so f of x, it's approximately negative x to the power 5. And then we want to put in some kind of analysis with x goes to infinity and x goes to negative infinity. So as you can see that as x goes to positive infinity, so y goes to negative infinity to the fifth power, so which is negative infinity. And then as x approaches negative infinity, so that means y goes to negative infinity, quantity to the power 5. So negative infinity to the power 5, which is considered negative infinity, and then times negative 1 outside of parentheses, so we do have positive infinity. So this one basically that describes the end behavior of the function. So you try to sketch the polynomial roughly, so to the power 5, so that means it's like 5 different changes. So on the x-axis and the y-axis. So as x approaches infinity, y goes all the way down to negative infinity, and then as x goes to negative infinity, so y goes to positive infinity. So we do have 5 different changes for the graphs. So this one will be considered decreasing, increasing, so 2 changes, and then decreasing somewhere here again, and then increasing, and then eventually it's going to be declining or decreasing. So as you can count it, 1, 2, 3, 4, 5 different changes for the interval. Again, this one is just a rough sketch. So this one is not required, but you just want to put in more analysis, more in-depth analysis for the polynomial. And then the next one is about multiplying the polynomial. So it's a trinomial. It's a quadratic trinomial multiplied by another quadratic trinomial. So the way that I usually multiply this, you can either FOIL or you can just simply regroup them. So you can distribute. So the first thing that you want to do, you want to regroup them. So negative 3n squared times the whole trinomial, the second trinomial. And then minus an times the exact same trinomial. And then plus 7, the constant term, multiplied by the exact same trinomial. And then the rest of this we can distribute. So negative 3n squared times 5n squared. So we do have negative 15n to the power 4. Negative 3n squared times negative an. So we do have positive 24n to the power 3. And then negative 3n squared times negative 3. So we do have positive 9n squared. And then the rest of this. So basically you want to repeat the same process, but you want to multiply by another term. So negative an times 5n squared. So that would be negative 40n cubed. Negative an times negative an, then that would be positive 64n squared. And then negative an times negative 3, so positive 24n. And then for the rest of those terms, so similarly, so just multiply them all together. So that one will be plus 35n squared minus 56n, and then 7 times negative 3 minus 21. So for the rest of those polynomial here, so we just want to combine the like term. So nothing's related with negative 15n to the power 4. So basically you just started with this. And then the one that is considered similar or like term, so you just want to either underline it or just combine them. So 24, negative 40, then that would be considered negative 16 n cubed. And then for the n squared, so 9n squared, 64n squared, 35n squared, just combine all those terms together. So 64 plus 35, that would give you 99. 99 plus 9, then that would be 108 n squared. And then 24n minus 56n, then that would give you negative 32n, and then minus 21. So eventually it's going to be considered a quartic 1, 2, 3, 4, 5 pentanomial. Again, from the highest degree to the least, the standard form. And now what about for the synthetic division? So synthetic division, you got to be careful with finding the divisor. The way to find the divisor, always set that the original divisor equals 0. And then we're using that a equals negative 7 over 2, solve for solve for a. So when can we use the synthetic divisions? Again, as long as the divisor is considered a linear binomial. So linear binomial, so we can use the synthetic division. So now for the dividend, we just want to bring down those coefficients. So we do have 2, 9, 23. Make sure that nothing is missing here. So 72 plus 52. So that one is considered a quartic pentanomial, 5 terms. And then divisor, then that'd be negative 7/2. So first number, always you want to bring down the first leading coefficient. So 2 times negative 7/2, then that'd be negative 7. Plus 9, then that'd be 2. 2 times negative 7/2, so that'd be negative 7 again. So 23 plus negative 7, so that'd be 16. 16 times negative 7/2, so that'd be negative 56. Combine it with 72, so we do have 16. So 16 times negative 7/2, so that would be considered negative 56 again. And then combine this all together, so that would be negative 4. So the remainder is negative 4. So you might be wondering, the quotient, is that just considered 2a to the power of 3 plus 2a plus 16? Well, plus 2a squared plus 16a plus 16. And then plus negative 4 all over the original divisor. Now a lot of people might be thinking about that this one is the final result. But this one is not the final result yet. Remember that the divisor is always considered 1 over, well, it's 2 times the quantity of a plus 7/2. So what we need to do, we need to multiply all those coefficients by 1/2. Because that 1/2 is considered the greatest common factor. So now distribute, so we do have a cubed plus a squared plus aa, and then plus 8. And then finally, plus the final remainder, which is negative 4, all over 2a plus 7. And that would be the final result of this whole process. And then for number 4, you want to find out the zeros by factoring. So one thing that we notice is the difference of 2 cubed. So difference of 2 cubed, we do have a cubed minus b cubed. So once you expand it or factor it, so we do have a minus b times the quantity of a squared plus ab plus b squared. And then for the sum of 2 cubed, we do have a cubed plus b cubed. So that will be considered the quantity of a plus b times the quantity of a squared minus ab plus b squared. So using that to factor form the difference of 2 cubes, so we do know that a is considered 2z. So again, if just trisect that az to the power of 3, it's like 2z times 2z times 2z. So negative 125 or positive 125, so that means b is considered 5. Again, trisect the number or take the cube root of that number. So using the pattern, difference of 2 cubes, so we do have 2z minus 5. And then times the quantity of a squared, which is 4z squared. And then times ab. Okay, so a times b, then that would be 10z. And then plus b squared, so plus 25. So the rest of this, we just want to set that equals 0. So that means z equals 5 over 2 for the real solution. And now what about for the imaginary solution? For the imaginary solution, we need to use the quadratic formula. So quadratic formula, so you can solve for z. So this one, you guys can finish that. So quadratic formula, which is negative b plus minus square root of b squared minus 4ac all over 2a. So you can find out one real solution and then 2 imaginary solution. Okay, so now to look at the last one. So using that p over q. So using that p over q to find out all the possible roots. Okay, we'll have to look at that here. Okay, let me just erase this one. Get some space. So for the given polynomial, we do have a cubic quadnomial. So for those who might be wondering, how do we find the possible rational zeros? Again, using the rational zero theorem, so p over q, so p, that means it's a constant. it's a constant term. So we need to find out all the possible factor of the constant terms. And then Q will be the leading coefficient. Okay, so here's P and here's Q. So what we need to do, so we just want to find out the possible factors of 6 over 1. So possible factor we have for 6 is plus minus 1, plus minus 3, no, plus minus 2, plus minus 3, and then plus minus 6. And then all over, possible factor of 1, then that would be plus minus 1. So there's so many possibilities here, so what you need to do, you want to perform the synthetic division, and then guess and check, and find out which one is going to work. So let's take out all those coefficients. So we do have 1, 3, 2, and 6. So let's start with the first attempt. So trial number 1, so I just want to start it off with x equals 2, or probably negative 2, or 3, or negative 3. So depending whether that you're lucky or not. So let's start it with x equals negative 3. So bring down the first coefficient. So we got 1 times negative 3, which is negative 3. So negative 3 plus 3, then that would be 0. 0 times negative 3, then that would give you 0. So 2 plus 0, then that would be 2. 2 times negative 3, negative 6. So the final remainder, 0. So anytime they see the final remainder is 0, so that means, so that root right there, it's considered the real root, or the rational root. So what we found, so it's x plus 3 times the quantity. So this one is always considered 1 degree lower. So it's x squared. There's no 0x, so that means just plus 2. Again, the remainder is 0. So now for the rest of this, set equal to 0. And then find out the rest of the imaginary solution. So that means x squared plus 2, so that equals 0. So x squared equals negative 2. Square root both sides. Again, we don't need this. So that means x will be considered positive, negative root 2i. Because that's considered quadratic, so 2 solution for the imaginary. So plus minus root 2i. Okay. And for those you might be wondering, what about the multiplicity? So let's say that we have an equation like this. So let's say we have a power 2 outside, so that means negative 3. So that would be the exact same solution that appear, well, which appeared twice. So multiplicity, that would be the power outside of parentheses here. And also for the imaginary solutions, so multiplicity would be considered 2 as well. So multiplicity for negative 3, so that appears twice. And the same thing happened with the multiplicity of plus minus 2i. So let's say we have an example like this one right here. Okay, so now for the rest of this, we'll take a look at that on the next part, the whiteboard right here. So for number 6, number 7, number 8, so that one is finding the original polynomial. Number 7 is finding that the remainder, evaluate the f of c by using the remainder theorem. And then number 8, using the Descartes rule. So we'll talk about that for the next part of the video today. So thank you for watching the first half.